So now we've already talked about the natural numbers and the whole numbers. So the next set of numbers that comes after that are the integers. Okay, so we denote the set of integers by this fancy z, and it's the union of the whole numbers along with their negatives. Right, so we have 0, then +1, +2, +3, so on and so forth, and then -1, -2, -3, and so on and so forth. So it extends infinitely in both the positive and the negative directions, okay? And in relations to the other sets we've seen, we have the natural numbers are a subset of the whole numbers, which are a subset of the integers, okay? So now that we know the definition of what countably infinite and uncountably infinite are, our question should be, are the integers countably infinite or uncountably infinite? So can we find some ordering of the integers that enumerates through the entire set of integers? Let's take a look. So let's list out our set of whole numbers, and it'll be evident why we use the whole numbers instead of the natural numbers in just a second. But since both the whole numbers and natural numbers are countably infinite, we could use either. Okay, so here's our set of whole numbers, and let's list out our integers. So now here we need to make a choice as to how we write out the set of integers, okay? I could write out 0, 1, 2, 3, 4, -1, -2, -3, -4, but this would make finding our bijection much more difficult, okay? We need some sort of pattern that as we crank out more whole numbers, we get the integers in some sort of ordered fashion. This will just make our bijection easier. Okay, so I'm going to write out the set of integers in a strategic way. So I'll write 0 first, then 1, then -1, 2, then -2, 3, then -3, 4, then -4, and so on and so forth. And this should make it a little easier to see the pattern. Okay, so what I want to do first is look at all the mappings from whole numbers that are even. I have 0 goes to 0, 2 goes to -1, 4 goes to -2, 6 goes to -3, 8 goes to -4, and so on and so forth. Okay? So it turns out that our function is piecewise in that we have multiple definitions for it depending on the input. And we notice that if x is even, our mapping from the whole numbers to the integers is dividing x by 2. Right? 4 goes to -2, 6 goes to -3, 8 goes to -4, so on and so forth. So that should be negative. So we divide our input by 2 and make it negative if it is indeed even. Now what's happening to our odd inputs? 1 goes to 1, 3 goes to 2, 5 goes to 3, 7 goes to 4, so on and so forth. Well, 7 is half of 8, 5 is half of 6, 3 is half of 4, and so on and so forth. So it looks like for our odd inputs, so when x is odd, we add 1 to our input and divide by 2. Okay, so this is our bijection between the whole numbers, and the integers. Is this indeed a bijection? Yes, because no two input numbers, so no two whole numbers, will map to the same integer, right? Because this function that we've described here is nothing but a mathematical instruction for this pattern that I've described up here. And clearly, no two whole numbers in this pattern up here will map to the same integer. As well, this pattern will eventually lead to any integer I want, right? So after this, I'll have 5, -5, 6, -6, and so on and so forth. And again, both of these sets are infinitely large, but if I continue this pattern forever and ever, I will eventually reach any integer that I care about, okay? So what we care about is that every integer is somewhere along this instruction. So we've essentially enumerated the set of integers, okay? We've ordered the set of integers. Cool. So that shows that the integers are countably infinite.